Corrosion is the unwanted oxidation of a metal. Oxidation of all metals in general is called corrosion, whereas oxidation of iron metals specifically is usually called rusting. Looking at the standard reduction table, near the bottom, we see that iron, zinc, and aluminum are all near the bottom right. They all have high oxidation potentials, which means they are strong reducing agents and are readily oxidized. But notice that aluminum and zinc don't seem to corrode like the iron in steel does. It's because aluminum and zinc both readily oxidize to form hard oxide coatings that are difficult for more oxygen to penetrate. So these metals will not corrode much under normal atmospheric conditions, even when they get rained on. But iron, or Fe solid, is different than other metals like aluminum and zinc. Its oxide does not form an impenetrable coating. Instead, it can flake off, exposing a fresh iron surface to oxidizing agents. Steel is mainly iron. Coating steel with tin protects its surface and prevents oxidation of the iron that's in it. This is why tin cans, which are tin-coated steel, are normally good for keeping food without rusting. However, if the cans are dented or pitted, the tin coating is broken and water can collect in the indentations. Now rusting occurs relatively quickly. We'll consider a piece of iron where a dent or a crack in a painted surface makes it easy for a water droplet to come in contact with the iron surface. Here, an iron atom can oxidize to an iron 2+ cation, which will dissolve in the water. The equation for this oxidation is Fe gives Fe2+ plus 2 electrons. Further oxidation of iron here causes pits in the surface to increase in size. What is formed here is an electrochemical cell. Because oxidation takes place here, this is called the anode region. Oxygen from the air can come into contact with the edge of the water droplet and the iron metal surface. If we could take this section of our standard reduction table and split it right here, we could add in this half reaction. It is the reduction of oxygen in the presence of water to produce hydroxide ions, and its reduction potential is positive 0.4 volts. Here, oxygen combines with water and the electrons formed by the oxidizing iron to form hydroxide ions, which then dissolve in the water droplet. Because reduction has taken place near the point where the water, iron, and air meet, this is called the cathode region. Looking at the solubility table, we see that Fe2+ and OH- form a low solubility compound. The Fe2+ ion formed at the anode can combine with the hydroxide ions formed at the cathode to produce the precipitate FeOH2, which can build up on the iron surface. What can happen is oxygen from the air and water in the droplet can act to further oxidize the iron in iron 2 hydroxide, and through a fairly complex series of reactions form what is called hydrated iron 3 oxide, which has the formula Fe2O3.XH2O. The X here means that a variable number of water molecules can appear in this formula, depending on conditions. Fe2O3.XH2O, or hydrated iron 3 oxide, is one of the major components of rust. The process that caused the oxidation of iron that we just discussed takes place when neutral or basic water contacts iron. The anode half reaction is the reverse of this one found lower on the reduction table, and the cathode half reaction is one we added to the table proceeding in a forward direction. Adding the cathode half reaction with its E0 value of positive 0.4 volts to the anode half reaction, which because it is the reverse of the one on the table, has an E0 value of positive 0.45 volts, gives the overall redox equation, a half O2 plus H2O plus Fe solid gives Fe2 plus 2OH minus, which has an E0 value of 0.4 volts plus 0.45 volts, which is positive 0.85 volts. The positive value for the E0 of the overall reaction means this process is spontaneous. Now, if the water contacting the iron is acidic, the cathode becomes this half reaction up here, which is a half O2 plus 2H plus 2 electrons gives water. The H plus here means acid is present. To determine the equation for the overall reaction and find its cell potential, we add the half reaction at the cathode, half O2 plus 2H plus 2 electrons gives water, with its E0 value of positive 1.23 volts, to the half reaction at the anode, which is Fe solid gives Fe2 plus 2 electrons, with its E0 value of positive 0.45 volts. And we get the overall reaction, a half O2 plus 2H plus iron gives Fe2 plus water, and its E0 value is 1.23 volts plus 0.45 volts, which is equal to positive 1.68 volts. We see that the overall cell potential for the reaction in acidic water is 1.68 volts. It is significantly higher than the overall cell potential in neutral or basic water, which is only 0.85 volts. This means there is a greater tendency for rusting of iron to occur when an acid is present than when it's not. In acidic conditions, iron tends to rust more readily. Recall that any oxidizing agent above Fe on the left will oxidize solid iron. So if iron is in contact with any of these, this will increase iron's tendency to corrode. This includes some common things, like all acids which contain H+ or hydrogen ions. Sulfuric acid in particular, with hydrogen and sulfate ions, nitric acid with hydrogen and nitrate ions, bromine and chlorine, sometimes found in hot tubs and pools, acidified oxygen, as we discussed before, and acidified hydrogen peroxide, H2O2. Rusting occurs more quickly when salt or other electrolytes are present. When salt or other electrolytes are added to water, the conductivity is increased, so charged particles can move faster. This speeds up the corrosion of iron. It is also known that chloride ions present in salt solutions tend to eat through any protective films that may exist on the surface of the iron, thus speeding up corrosion. In wintertime, salt is spread on roads to melt ice and snow. Salty water that is splashed on vehicles can greatly increase the rate of rusting if they are unprotected. We should also point out that as temperature increases, the rate of corrosion also increases. All reactions increase in rate as the temperature increases. A type of corrosion we should be aware of is something called galvanic corrosion. Galvanic corrosion results when two dissimilar metals are attached in the presence of an electrolyte. For example, let's say we have two pieces of steel, which is mainly iron, bolted together with bolts made of copper or an alloy of copper. We add some salt water, which is an electrolyte. This establishes a type of electrochemical or galvanic cell, in which the metal lower on the reduction table, the iron in this case, becomes the anode and undergoes oxidation, which slowly causes the steel to corrode where the bolts contact it. Galvanic corrosion can also happen when a brass boat propeller is used in salt water. If we take a closer look at the brass, we see that it is an alloy of mainly copper and zinc. Because zinc is lower on the right side of the reduction table, it is a stronger reducing agent and is more readily oxidized than copper. You may recall that zinc normally forms a protective oxide layer. However, salt water tends to penetrate through this layer, making zinc more susceptible to oxidation. Zinc atoms on the surface oxidize to Zn2+ ions. These ions will leave the zinc and dissolve in the surrounding water, gradually corroding the brass propeller. To summarize, corrosion of iron can be caused by exposure to oxygen and water, exposure to stronger oxidizing agents than Fe2+. These are the species on the left side of the table above Fe2+. Or being attached to a metal higher than Fe on the table in the presence of an electrolyte. This is called galvanic corrosion. And corrosion is enhanced by the presence of acids, the presence of an electrolyte like salt water, and higher temperatures.